Hi, I'm Jim Curran. Today's lesson is going to be about rates of change, applied rates of change, and then we're going to do a few examples with rates of change. I hope you enjoy today's lesson. Today we're going to talk about rate of change. A rate of change statement needs to have two quantities specified. First, we need to talk about what quantity is changing and what this quantity that is changing with respect to. With respect to what is it changing? And a note here says often we are measuring the rate of change with respect to time. Sometimes this isn't even mentioned. So if we're talking about change in distance with respect to time, we'd be taking dt. If we're talking about change of distance with respect to time, it would be change in distance over or with respect to change in time. Now let's talk about rates of change and their signs. First, let's consider a positive rate of change. If we have a positive rate of change over some interval from A to B, and that's in the x-axis, then y increases from A to B. So as x increases, y increases, and we see we have a dy dx, or derivative. How is y changing with respect to x? That's going to be a positive rate of change. As x increases, y increases. Continue on with our discussion of rates of change and their sign. Here we see a negative rate of change. Over the interval from A to B, as x increases, y decreases. And we see we have a dy dx. The change in y related to the change of x is negative or less than 0. We've just talked about positive rates of change and negative rates of change. Here's our third case, 0 rate of change. We see y remains constant as x increases. So we're not having any fluctuation vertically as x increases. This is 0 rate of change. And dy dx is equal to 0. We've just talked about rates of change. Let's talk about how do we apply these rates of change. First, let's look at an application to economics. There's the key I drew there. The key is that x, in all these cases, with respect to what? We're changing with respect to x. And x is the number of items produced, always. Cost function, how much money is going out of our pockets, is labeled capital C of x. Well, dc dx is the marginal cost. Our cost, the change in our cost compared to the number of items produced. The revenue function, r of x, that's how much money is coming in. Well, we can look at the change in revenue per number of product that is being produced. That's the marginal revenue. And the profit function is revenue minus cost, or P of x. Profit does equal the money coming in minus the money going out. Profit function is P of x. Well, dP dx is how does our profit change compared to the number of items produced. And that's also called marginal profit. Let's do a problem using the application of rate of change. Here we have a problem that says the cost in dollars of manufacturing X units of a product is given by C of x equals x cubed minus 20x squared plus 300x plus 1000 for x is greater than or equal to 0. If each item sells for $300, find the marginal profit when 100 units are being manufactured. First of all, we have to remember that profit is equal to revenue minus cost. So we have that in mind. Well, we know that revenue is going to be $300 per item. So 300 times the number of items will give us 300x. We know that x is the number of items. And we also know the cost. So we can set profit equal to the revenue minus the cost, which will be x cubed minus 20x squared plus 300x plus 1000. I have that, which I can simplify when I distribute out the x and combine like terms. Profit is equal to negative x cubed plus 20x squared minus 1000. That's distributing out this negative and combining the like terms. So I want to find marginal profit. You have to know that marginal profit is going to be dP dx, where x is the number of items manufactured. Okay? Well, another way to say that would be, I'm looking to find P dash of x. p dash of x is going to be negative 3x squared plus 40x. I get that from there and there. Well, let's find the marginal profit. Here's our general statement for marginal profit. Let's find the marginal profit when 100 items are produced. Simple. P dash of 100 equals negative 3 times 100 squared plus 40. 40 times 100, which gives me negative 26,000. There is our marginal profit. See, it's not a good profit. It's a loss when 100 items are produced. Here's another example of an application of growth rate, or rate of change rather. Here's another example of a rate of change problem. I think the key to these problems is understanding what rate of change means. It means take the derivative. The population of mosquitoes in a controlled laboratory experiment is modeled by the equation P of t equals 250 e to the 0.09 t, where t is greater than or equal to 0, and t is in days. Find the growth rate of mosquitoes after 5 days. Fine. Find the growth rate. It should be ringing in your ears. You must find the derivative. You should be thinking chain rule here. So we get P dash of t is equal to, ultimately, 22.5 e to the 0.09 t. We want to find the growth rate of mosquitoes after 5 days. Well, that's simply plugging in a 5 for t. 22.5 e to the 0.09 times 5, which ultimately, when we analyze that, we get 35.3. What is that? It's mosquitoes per day. And look at, I've got 3 significant figures in my answer. Let's consider now another application of rate of change, and that is to kinematics, which is the study of motion. If I consider our original function x of t, in other words, how does x change relative to t? X being position. I have change in x versus t, where x is position. And the function is x of t. Consider a particle with a point mass having a displacement of x as x of t. That's our displacement. This distance here is x of t from a stationary origin, we'll say. Well, if our displacement is x of t from a fixed point O, then instantaneous velocity is going to be the first derivative of displacement. V of t is dx dt, change in position relative to change in time, which can be seen as the first derivative of our original displacement function. Here's our original displacement function, x of t. Here's our velocity, x dash of t. Well, how does velocity change with respect to time? That's acceleration. Instantaneous acceleration is measured dv dt, or take the derivative of velocity. In other words, that's the second derivative of our original displacement function. Here you can see the graphs. If I take the derivative of position versus time, or displacement versus time, I get velocity versus time. If I take the derivative of velocity versus time, I get acceleration versus time. You have to be careful with displacement, velocity, and acceleration because the signs are significant. With displacement, here, if the point P is to the right of our point O, then our displacement is positive. If x is greater than 0, our displacement is positive. That means P is to the right of O. If x is less than 0, in other words, if our displacement is negative, that means P is to the left of O. And if x, the displacement, is equal to 0, that means that P is at our point O. Let's consider now velocity, which is the derivative of our displacement. If velocity is positive, we see that that means that P is moving to the right. If velocity is negative, that means P is moving to the left. And if velocity is equal to 0, that means P is stationary. We can now consider acceleration. Acceleration is the change in velocity to the change in time. Acceleration. If acceleration is positive, that means the velocity is increasing. Because again, acceleration is measuring the change in velocity per time. If acceleration is negative, less than 0, that just means the velocity is decreasing. And if acceleration is equal to 0, that just means the velocity is not changing. You could be going 60 miles per hour consistently and your acceleration is 0. That doesn't mean you're stationary. It just means that your velocity is not changing. Again, important to consider the signs in kinematics. A positive, yes. Here's a good example of a problem, very straightforward, involving kinematics. And it's asking, can you apply the rates of change? A particle is moving in a straight line relative to some origin O and has a displacement s meters after being in motion for t seconds governed by the equation s is equal to t cubed minus 4t plus 2. S is our displacement relative to time. Find its velocity. Well, that's going to be s prime, which is equal to 3t squared minus 4t, minus 4. I just found the first derivative. The first derivative of displacement is velocity. That's the velocity. Find its acceleration? Well, that's going to be the second derivative, which of course is just 6t. In the second part it says, describe its motion. Well, what I did is I used my handy-dandy graphing calculator and I graphed its motion, its displacement. And I get this. Well, how do we interpret that? It gets tricky. It's positive, 0, negative, 0, positive, which means it starts to the right of O, goes to O, goes to the left of O, stops, turn around, go back to O, and then to the right of O. Remembering in our last slide, positive displacement just means we're to the right. Negative displacement means we're to the left. Here we have positive displacement all the way down to 0 displacement. Here we have negative displacement, back to 0 displacement. Here again we have positive displacement. It's kind of difficult interpreting a two-dimensional particle in an XY grid. Actually, it's a one-dimensional particle in a two-dimensional grid.